All right. Okay. So happy Monday, everybody, and we're gonna get started on just some basics of Bayesian statistics and just some general ideas there, and this will kind of form I guess a framework on which we are going to later apply Monte Carlo methods. But in the beginning, we're going to just kind of look at Bayesian statistics, and you don't need Monte Carlo methods at all in the beginning when you do kind of some with Bayesian statistics and a lot of concepts there. You don't need to use Monte Carlo methods at all. But I kind of just want to get us started there. And all right, so let's take a look. So I'm going to present a lot of this as kind of a contrast to frequentist statistics, and I'm assuming kind of all of you have your frequentist statistics background. You know, a lot of the, your intro stats class. You know, if you took AP stats or if you took stats 10 at UCLA, or pretty much every intro stats class is taught from a frequentist perspective. And in that frequentist perspective, probability is defined as the long run relative frequency of an event, okay? And so when we say something like this coin has a probability of landing heads equal to 0.5, what we're saying is that in the long run, meaning that after something that approaches infinity, the relative proportion of heads that we observe will approach 0.5. Okay. And when you do maximum likelihood estimation, and when you create confidence intervals, those are both frequentist statistics ideas. Okay. And so, when we're talking about data or probabilistic models, is that you've got some kind of model that is responsible for generating the data that you have observed. And that model is going to be defined by parameters. So for example, if you have a coin, there is the coin is defined by some proportion P, okay? Probably it's 0.5, okay? Like we would say the proportion is 0.5, and so that when I flip the coin, it will land heads 0.5 and land tails 0.5, and that's going to be what's responsible for generating our data. If we're talking about a normal distribution, that normal distribution is defined by parameters mean mu and variance sigma squared, okay? Here, I've got, for an example, I've got this box, and inside this box, I have some marbles in it, okay? You're not allowed to see what's inside the box, but when I draw a marble out, some of these marbles are blue, okay? And then other marbles are not blue, okay? And I might say, what's the proportion of marbles that are blue, okay? And so inside this box is defined by some parameter theta, which will be the proportion of marbles that are blue inside the box, okay? And so let's say we play this game and I reach into the box multiple times, okay, with replacement. And let's say I draw 10 marbles out, and 6 of those marbles, and let's say 6 of those marbles are blue, okay? So if I draw 10 marbles and 6 happen to be blue and the rest are not, the question is, what is the maximum likelihood estimate for the proportion of marbles that are blue? What's the maximum likelihood estimate for the proportion of marbles that are blue? Okay, and so the way maximum likelihood estimation works is that, well, you say, all right, let's define some, let's create the likelihood function for the data that we have observed, right? And so in the case of drawing marbles with replacement out of some kind of box, we could use either a product of Bernoulli observations, or we could just go straight to the binomial distribution, okay? And so in our case, I'm going to just go straight to the binomial distribution. And what we want to do is we want to find the value of theta that is going to maximize the likelihood. So the likelihood function is that we have observed 6, I guess this should be x equals 6 and n equals 10. So out of 10 marbles, okay, 6 of them are blue. And the binomial probability of this data that we observed, or the likelihood, binomial likelihood for this data, is going to be theta raised to the 6, theta being that unknown proportion, theta raised to the 6 times 1 minus theta raised to the 4th. Okay. And to find the maximum, what we're going to do is that you're going to take the derivative of this likelihood function. You take the derivative with respect to theta, and you are going to take that derivative, set it equal to 0, and solve for theta. Oh, look, I'm able to now, okay, I just uploaded, CCLE reloaded for me, and I was able to upload the PDF that I have on the screen right now. So if you want to go to CCLE and download the PDF, it just went up, although, all right, it just crashed on me again. So, but I think it's up there. I think the PDF is up there if you're able to, if you want to try to get it. But yeah, CCLE seems to be having issues right now. Okay. Yeah, I imagine. I don't know. I wonder if they just scheduled classes whenever people felt like it, and then said like 10 o'clock's kind of a popular choice. Because normally on campus, a lot of times our classes are scheduled at times that the instructors don't want, because there's a limitation on classroom space. And so you just kind of, the classrooms basically get used from 8 a.m. to 5 p.m. And you just get whatever classroom spot that gets allotted. But now that it's all online, you can just say, well, 10 a.m. is my favorite time. And if all the instructors pick 10 a.m., then something like this could happen. And then the entire campus, the entire student body is pinging the CCLE at 10 a.m. I don't know. Who knows? But okay, all right. Anyway, so this is our likelihood function, and we're going to go ahead and maximize it. And the thing about products is that taking the derivative of a product can get messy. And so a lot of times what we do is we take the log of the function. You take the log of a function, it turns the product into a sum, and it's a lot easier to take the derivative of a sum. So the log of this thing is going to be, so 10 choose 6 is 210, so it becomes log 210 plus 6 log theta plus 4 log 1 minus theta. You take the derivative of this with respect to theta, and you get 0 plus 6 over theta plus 4 over 1 minus theta multiplied by -1 because of the chain rule with the negative theta here. And then you solve for theta. Okay, you set that equal to 0, solve for theta. So I'm going to bring 4 over 1 minus theta to the other side is equal to 6 over theta. Multiply both sides by theta times 1 minus theta. And here we get 4 theta equal to 6 times 1 minus theta. 10 theta is equal to 6, and theta is equal to 0.6. All right. And so this is going to be our maximum likelihood estimate. And that kind of aligns with our intuitive sense that if I've taken 10 marbles out of the box, again, it's so loud, 10 marbles out of the box, and if 6 of them are blue, then it makes sense that kind of our estimate of what proportion of the box is blue would be 0.6. That kind of makes sense here. And according to frequentist statistics, we will say, all right, well, my estimate for theta is 0.6. And I can just use this estimate for future estimates, future calculations. So I could ask, what is the probability that if we draw 3 more marbles from the box with replacement, what is the probability that we're going to get exactly 2 blue marbles? All right. So that's a binomial question, and the answer is going to be 3 choose 2, 0.6 raised to the 1, and 1 minus 0.6 I'm sorry, 0.6 raised to the 2 and 1 minus 0.6 raised to the 1, okay? Because we need 2 blue and 1 that's non-blue. And so you just kind of plug in that estimate of 0.6 into the binomial question. And when you do that calculation, you get 0.432. Okay, let me just pause here. This is all frequentist statistics and a little bit of review. So I'm going through it quickly, but I just kind of want to pause and make sure everyone's okay. And if you have any questions, throw them in the chat or raise your hand. I think our classroom is small enough where if you wanted to just unmute yourself and ask a question, you can do that as well. Now we're feeling all good. Okay, all right. So let me delve in a little bit more on frequentist reasoning. And when you create a confidence interval, right? So let's say I make a confidence interval, and I've completely made this up, but let's say we make a confidence interval for theta, and it goes from 0.51 to 0.69. Okay. And I don't know, did I ever do this coin flip example? But when you do a confidence interval, you have to say, I am 95% confident that the proportion of marbles that are blue in the box is between 51% and 69%, okay? And you are not allowed to say that there's a 95% probability that the proportion is between 0.51 and 0.69, okay? Did they teach you that you're not allowed to say that there's a probability, that it's a probability, but you have to say I'm this confident, okay? And the reason for that is that the proportion of blue marbles is a fixed value and doesn't vary. And it only makes sense to talk about probabilities when it's something that is subject to randomness, right? So if I talk about, here's a coin and I'm going to flip it, what's the probability that it lands heads? Okay, we can say, okay, the probability that the coin landed heads, or that the probability that the coin will land heads is 0.5. But once I've flipped it, if I ask the question, what is the probability that the coin has landed heads? What's your answer there? So once the coin has been flipped, the question of what is the probability that the coin has landed heads becomes a nonsense question, because it either landed heads or it didn't land heads. And there's no more uncertainty, okay? It either did or it didn't land heads. And so it doesn't make sense to talk about there being a probability that it has landed heads or it hasn't. It either did or it didn't. You don't know how it landed. So you have to say, I'm 50% confident that it landed heads. I'm 50% confident that it landed heads, but you can't say that there's a 50% probability that it landed heads, because it either did or it didn't land heads. Okay, that's the frequentist reasoning. That's the frequentist reasoning. Okay. However, when we're talking about Bayesian statistics, okay, the unknown parameter, okay, so when we're talking about the proportion of marbles in the box is not treated as a fixed value. Instead, we treat the unknown parameter as a random value. Okay, so the unknown parameter is treated as a random value, and now you can talk about the probability of the proportion being between 0.51 and 0.69. So this was not allowed. This sentence right here, when it was frequentist statistics, this sentence was not allowed, okay, because the proportion is a fixed value with no uncertainty, okay? However, in Bayesian statistics, the unknown parameter is not fixed. The unknown parameter is a random variable. And if it's a random variable, then you can talk about probabilities associated with it, right? And so, when we're talking about a box of marbles, maybe it doesn't quite make sense to talk about the treating the proportion of blue marbles in this box as a random variable, because technically at any point in time I could take the box, dump it out, and count up all the marbles, and then there would be an exact value for the proportion that's blue. Okay, and it probably doesn't quite make sense to say that proportion is a random value, because I could, maybe I could just dump out the marbles and I would get an exact value. Okay. However, if we're talking about something that's subject to random changes, maybe it does make sense to talk about that kind of parameter or proportion to be a random variable. Okay. So for example, what if we're talking about what proportion of the United States are under the age of 18? Okay. What proportion of people in the United States are under the age of 18? Okay. The exact proportion of people under the age of 18 is subject to kind of random events, right? People are born, okay, that's +1 to the kind of number of people who are under 18, okay, and then people die, and if it's an adult who dies, then you're subtracting values, and then people age, and so some people are 17 and then they turn 18 and things like that, and so so the exact proportion of how many people what proportion of people in the United States are under the age of 18, this is going to kind of change a little bit randomly every single day, right? And so if we're talking about this proportion, it kind of makes sense to treat it a little bit like a random variable, right? It's a variable that's going to be subject to some random forces. So in that case, it kind of makes sense to treat it as a random variable. If we want to go back to this box, okay, and talk about what proportion of the box is blue, maybe it could make sense to talk about the probability, or treat it as a random variable if we treat probability as a subjective belief, okay? So rather than treating it as the long run frequency, we can talk about probability being, what do you believe about the proportion in this box? Do you believe the proportion to be 0.5 or 0.6 or 0.3 or some other value, okay? And maybe we can say, you know what, you're never allowed to look in the box. You're never allowed to dump out the contents of the box. You will never be able to count the number of marbles that are actually inside the box. And in that case, if it's kind of this, we're never allowed to get the real answer, then it just has to be like, what do we believe is inside the box, okay? And so in that case, we could treat probability as a subjective belief that might differ from one person to another, but it's a belief about what we believe kind of to exist inside the box. Is this okay? All right, thank you for that thumbs up there. All right, and so and so we're going to treat the parameters as random variables, and in Bayesian statistics, when we treat the parameter as a random variable, the parameters themselves will have their own probability distributions, okay? And so questions and calculations that depend on the parameter are going to become a lot more complicated, because the parameter is no longer just a single value, okay? But is now associated with a distribution. So I'll show you an example of what I mean by this, okay? And to some extent, I do believe that despite the more complicated calculations that get involved in Bayesian statistics, I do believe that in a lot of cases, the Bayesian approach is a lot more reasonable than the frequentist approach in certain cases, right? So, so if we go back to our example, what I was saying was that, let's say we took 10 marbles with replacement out of the box, and 6 of those marbles were blue, okay? According to the frequentist approach, we do maximum likelihood estimation, and the proportion of blue marbles in the box is estimated to be 0.6, right? And so, we can create a confidence interval and put kind of a margin of error or error bars around this estimate. But basically, whenever you do calculations in the future, you're just going to assume that the proportion is 0.6, right? So when we went back here and I said, what's the probability of getting 2 blue marbles out of 3 marbles in the future? Okay, based on my maximum likelihood estimate, I just plug in 0.6 and I get an answer here. Okay, but you know, and maybe this is just me, but the idea of just settling in on a single value like 0.6 after observing only 10 observations feels a little strange. Okay, it feels a little premature to just say, all right, the proportion's 0.6. I observed 10 things, and now I'm convinced that the proportion is 0.6, and we're going to just use that for all future calculations. Okay, with the Bayesian approach, we are going to say that the proportion of blue marbles has a probability distribution. Okay, after observing our data, we're going to say, you know what, the probability distribution representing the proportion of blue marbles will have a peak at 0.6, will be tallest at 0.6, but we'll also have, you know, maybe the proportion in the box that's blue isn't exactly 0.6. Maybe it's something closer to 0.5, or maybe it's 0.65. Maybe it's something around 0.6. Maybe it's a little bit off, okay? And by taking that, we acknowledge the data that we've seen, okay? And we saw 10 marbles and 6 of them were blue. So we're going to acknowledge that by making a probability distribution with a peak at 0.6. But we're also going to kind of acknowledge the possibility, something just happened. We're going to acknowledge the possibility that the proportion could be something other than 0.6 rather than just zeroing in on that value. And so, you know, this next slide, maybe this could represent what the probability distribution looks like, saying that, you know, a proportion of 0.6 is highly likely, but you know what, maybe the proportion that's blue could actually be 0.8. Maybe the proportion that's blue is actually as low as 0.4, and just I happen to get a sample of 10 marbles that had more blue marbles or fewer blue marbles than what's actually in the population. Okay, and this will make the calculations complicated because now I have to say, well, what's the probability? We have to kind of take into account all of these different possibilities. So yeah, the trade-off is that the calculations are a lot more complicated. If we want to answer this question, you know, what's the probability of getting 2 blue marbles out of 3 marbles? Okay, for frequentist, we just plugged in 0.6. We said, I'm convinced that theta is 0.6, and we just plug in our number and we get this, okay? For the Bayesian answer, we have to kind of go back and say, well, theta could be 0.6, theta could also be 0.5, theta could be 0.51, theta could be 0.4778, theta could be any one of these possible values, okay? It's quite unlikely that theta is 0.01, okay? It's unlikely that theta is 1%. But I mean, it could be. And so, you know, we're going to plug in every single possible value. And then, you know, for theta equal to 0, like 1%, we would just give it a very low weight, you know, when we kind of calculate it. Whereas theta being 0.6 will be weighted heavier. Theta being 0.7 will also be weighted kind of heavy. You know, theta being 0.9 will be weighted less, right? And so we would consider every single possible value that theta could be, and we're going to kind of weight the resulting calculation by that probability, okay? And so you end up getting an integral that we have to solve. And we'll work through these calculations a little bit later, not today, but we'll work through them later. But it's kind of the idea that theta, the proportion of marbles that are blue in the box is not going to be just assumed to be a single value, but it's going to follow some kind of probability distribution. All right, and so I'm going to start introducing what's known as the beta binomial model, and I think first we're just going to have to talk about the beta distribution. Okay, and this is kind of a very common example that we use when introducing Bayesian statistics, just because it's got some nice properties. And to introduce this, I'm going to use an example from baseball. Okay, so And I have to give credit to this website, Variance Explained, that inspired this example here. Okay. So, I don't know if you guys watch baseball or not, but in baseball, one of the statistics that we track for players, or at least batters, is batting average. Okay. So in baseball, generally you divide your players into batters and pitchers. Okay. And pitchers are not expected to be able to bat. Okay. Their job is to throw the ball. But the batters are the ones that have to hit it. And batting average is considered, is calculated by doing hits divided by an at-bat. And forgive me for, mansplaining here, but so if you're totally unfamiliar with baseball, okay, a hit is considered when the batter hits the ball and manages to get to base. Okay, so if the bat makes contact with the ball, but the player is out, or it's a foul or something like that, it's not considered a hit. Okay, so the batter has to make contact with the ball and manage to run to base, and that's going to be considered a hit. Okay, there's other things, based on balls and stuff like that, but it's basically hits divided by at bats. At bats is kind of like a plate appearance. It's a little bit different, but you can think of it at that. Okay, and in Major League Baseball, so in the U.S. and kind of the professional baseball players playing Major League Baseball, and pretty much all of the batters will have a batting average of higher than 0.2. Okay, so they are expected to get on base at least 1 out of 5 at bats. Okay, and if a player's batting average dips below 0.2, they're most likely to get kind of cut from the team or get pushed down to AAA or something like that. Okay, you might have a few players that fall into a slump and dip below 0.2, but in general, the batting average is expected to be above 0.2. Okay, however, at the same time, kind of almost everyone is going to have a batting average below 0.3. All right, batting averages in baseball follow this really narrow range on kind of the number line. Okay, the highest career batting average of all time. Okay, so if you go on the internet and if you type in highest batting, we'll say career batting average ever. Okay, that's Ty Cobb with a batting average of 0.366. Okay, 366. So batting averages in baseball, you just read them as the numbers. So this is, say, the player's batting 200, the player's batting 300, and the highest batting average is 366. Okay, that's the highest of all time. Okay, and if a player has a batting average of 330, 0.33 or higher, that's like 1 out of 3. That's considered to be very, very, very good. That'll be kind of like one of your best players is a player with a batting average like this. Okay. And so let's say a team gets a new recruit. Okay, hires a new player, bumps somebody up from AAA or something like that. Okay, and we don't quite know what this player's batting average is going to be. So right now, the player's batting average is unknown. And let's say in his first 10 at-bats in Major League Baseball, the player manages to get 5 hits. Okay, so 5 hits out of 10 at-bats. And so his batting average so far is 500. Okay, 0.5. 5 divided by 10. His batting average so far is 0.5. And so according to Frequentist statistics, if you go through the maximum likelihood estimation, your estimate for the player's batting average is going to be 500. It's going to be 0.5. All right. But our gut intuition tells us that by the end of the season, that the player is not going to be able to sustain this batting average of 0.5 through the entire season, and that by the end of the season, the player's batting average is going to be a lot lower than 0.5. Maybe it'll be like 0.3. Maybe this is like a really good player and manages to have a season batting average of 0.3 or 0.33 or something like that. But our gut and our intuition tells us that there's no way that the player can maintain this batting average of 500 throughout the entire season, because we know that the kind of the highest of all time for a career batting average is 0.366, right? So there's something that tells us that I doubt that somebody's going to have a batting average this high. Okay, does that kind of make sense? Just your kind of your gut feeling about this? All right, and so how can we approach this mathematically, right? How, rather than just saying like, it's not going to happen, okay? Rather than just saying, you know, I know stuff about baseball, and you know, to assume that somebody's going to have a batting average that stays at 500 throughout the entire season, that's an unreasonable thing. Can we do something mathematically? Can we express this kind of intuition about a player's batting average in a more mathematical approach? And so we can do this by creating what's known as the prior distribution. And so what we're going to say is, we're going to say, you know what, this is what the distribution should look like for a player's batting average, okay? We basically want almost all of the values to be above 200 or 0.2, and most of the people to be below 300 or 0.3. And there should really be no one who has a batting average of around over 400, okay, or 0.4. And so we can create this. This might reflect our distribution of what we believe batting averages to be, okay? So prior to looking at anything that the player does, we're going to say the batting average should be between 0.2 and 0.3 something, okay? What is this? Okay. And so a distribution that we can use to express basically a proportion between 0 and 1 is the beta distribution, okay? So the beta distribution is a continuous distribution defined on the interval 0 to 1, and it's frequently used to kind of model a proportion, especially a random proportion, because proportions are always defined on the interval 0 to 1 as well, okay? So sometimes we call the beta distribution a distribution of proportions or distribution of probabilities, because it's always between 0 and 1. And so if you have some random variable theta, okay, the PDF of random variable theta that follows a beta distribution, the PDF is going to be this, okay? 1 over beta function alpha beta, theta raised to the alpha minus 1, and 1 minus theta to the beta minus 1. And this thing, beta, the beta function alpha beta is gamma alpha times gamma beta divided by gamma alpha plus beta. Okay, so this looks scary. This thing looks scary, but it's just a constant, okay? This is just some constant. It's not, and this constant, it has only one purpose, okay? And that's to make sure that when you take the integral of this, right, the integral of all PDFs have to integrate to 1. Okay, and so this is just a constant, so that whatever numbers you plug into here, okay, if you plug in alpha equal to 100 or alpha equal to 2 or alpha equal to 0.1 or whatever it is, whatever numbers you plug into alpha and beta here, the resulting function has to integrate to 1. And the way it's going to integrate to 1 is via this constant, okay? And so don't worry about the gammas. It's just to make sure that the PDF integrates. Okay. And a little bit of intuition to kind of think of these shape parameters. I think in R, alpha is called shape 1 and beta is called shape 2. They're basically 2 shape parameters. Is that you can kind of think of this as how many yeses we've seen and how many nos we have seen so far. Okay. And the resulting beta distribution will then kind of reflect the probability of getting a yes, right? And so you'll have a peak around alpha divided by alpha plus beta, which is kind of the proportion of yeses out of the total yeses and nos you've seen. And then if the total of alpha and beta is small, which means you've only observed a few yeses and nos, it's going to be more spread out. And if the total of alphas and betas is high, which means you've seen a lot of yeses and nos, the spread is going to be, you'll have less spread there. Okay, and so I'm just going to show you a bunch of examples of the beta distribution for you to get kind of a feel for what the beta distribution looks like. But there's lots of these things. Okay, so this is a little hard to see. This is the uniform distribution. Alpha equal to 1 and beta equal to 1 is equivalent to the uniform distribution from 0 to 1, meaning all values from 0 to 1 have the same probability. Okay. If you have alpha equal to 2 and beta equal to 2, you get this distribution. Okay, so the most likely value is 0.5. And then, again, the distribution is defined on the interval 0 to 1. Okay. If I set alpha equal to 5 and beta equal to 5, so this would be equivalent to saying I've got my box of marbles, and I've drawn 10 marbles out. 5 of them are blue and 5 are not. Okay, and if 5 are blue and 5 are not, what's kind of the probability for the proportion that's blue? Okay, what's the proportion that's blue? 5 out of 10, 0.5 is the most likely one, but we're going to say, yeah, it could be as high as 0.7 or 0.8 or as low as 0.3 or 0.2. And any of those values seem reasonable for getting 5 out of 10 marbles to be blue. Here is alpha and beta are both equal to 20. So again, if I keep drawing marbles out of this box, right, and if we've observed 20 blue marbles and 20 that are not blue, what's the proportion that's blue in the box? Okay, again, if 20 are blue and 20 are not, for a total of 40 marbles being observed and 20 are blue, the most likely probability is around 0.5. Okay, but we also can acknowledge that the proportion could be as low as 0.4. Okay, 40% blue, and if it's 40% blue, just by random chance, I could get 20 blue out of 40 marbles. If the proportion is something like 0.6, it's also possible to get 40 marbles where 20 are blue. Okay, but if the proportion is 0.9, okay, we're basically saying I don't think the proportion in the box is 90% blue, because getting 90% blue or having 90% blue, it would seem really strange to get 40 marbles where only 20 are blue. Okay, so that's kind of what's happening. So with alpha, as I draw here, if I have alpha equal to 50 and beta equal to 50, I have a distribution that looks like this. Okay, it gets more narrow to indicate that now that I've seen 50 blue out of a total of 100 marbles, 50 plus 50 being 100, kind of the range of what I believe to be the proportion of blue marbles on the box gets smaller and smaller. Okay. If I have, so here's alpha equal to 1 and beta equal to 99, I have this very skinny distribution, right? And so, so this would be something like, I've drawn a whole bunch of marbles out of the box. I've drawn 100 marbles, and so far I've only seen 1 marble that's blue. Okay, so if I see only 1 marble that's blue, then the proportion that's blue in the marble is going to be something very close to 1% or 0%, something very low over here. Okay, and so I have this peak over here, and it's very unlikely for the proportion to be something like this. Okay. We have a question that says, how is density calculated? Okay, the density, again, is calculated using the PDF, right? The density is calculated using this PDF. So we're just plugging in different possible values for theta, and we're raising it to the alpha minus 1 and the beta minus 1. Okay, and again, this constant here, this 1 over beta alpha beta, is just to make sure that the integral, that if you take the integral of this, the entire area of this thing, that the entire area is 1. So as it gets skinnier and skinnier, you'll notice that the upper cap gets higher and higher, okay? Because the total area has to be 1, right? So this total area is 1, the total area under here is 1. So as I get more narrow, it has to get taller and taller in order to make sure that the area is equal to 1. So this is alpha equal to 1, beta 99. If I say alpha is 2 and beta is 98, you know, we get a peak that looks like this. Alpha 5 and beta 95, we get kind of, you know, the peak is something around 0.5. Here's alpha equal to 10 and beta equal to 90, and we can see kind of the proportions sliding up. So if you've drawn 100 marbles out of the box, 10 of them are blue, what's the proportion you believe to be blue in the box? It's going to be something close to 10%, but you know, you could acknowledge that it could be higher, like 15%, could be lower, like 8% or something like that. Okay. And so as I select different values of alpha and beta, okay, so here's alpha equal to 40 and beta equal to 60, we get a kind of a distribution that's centered around 0.4. All right, let me also just kind of show you what happens as so right now the sum of alpha and beta is 100. If I kind of keep this, this ratio of 7 to 3 the same, and I just decrease that sum, so instead of 70 and 30, let's say I do 63 and 27. So this is still a 7 to 3 ratio, okay? We can see that comparing the 70 and 30 to the 63, 27, we can see it gets a little bit wider, okay? And as I decrease these numbers, keeping the same ratio, it's going to stay centered at 0.7. It's going to stay centered at 0.7, but it's going to get wider and wider, right? So here's 70 and 30, 63, 27, 56, 24, 49, 21, 35, 15. It gets wider, 21 and 9, okay? And if here I'm going down to 7 and 3, and we can see it gets wider and wider, okay, even though kind of the peak still remains around 0.7. Okay, and going in the opposite directions, so if I keep this ratio of 7 to 3 the same, but I increase it to say 140 and 60, 350, 150, 700, 300, we can see it gets skinnier and skinnier and taller and taller. Okay. Question says, why are the density values integers instead of proportions like relative frequency? So that's just kind of how the beta distribution is defined. It's defined by these two shape parameters, alpha and beta, and they don't have to be integers, but they don't represent proportions. They represent what we call pseudo counts, kind of like if you've seen the number of yeses and the number of nos, right? So if I've observed a total of 150 marbles, and 350 are blue and 150 are not blue, then what's the proportion that we believe to be blue in the box? Something around 0.7, right? 350 divided by 500 is something around 0.7, but we acknowledge that it's also possible for the proportion of blue marbles to be something a little bit higher, right? The proportion could be, say, 73% in the box. And even if the box was 73% blue, could it produce our sample where it was 70% blue, 350 out of 500 blue marbles? And the answer is yes, right? And so this kind of represents kind of a range of, I guess, reasonable values for that proportion of blue marbles in the box. I don't know if that helps, okay? So keep in mind, theta is defined from 0 to 1 because it represents the proportion. It represents the proportion of either blue marbles or the proportion of success or the proportion of whatever it is, the probability of something. And so it's going to be defined only from 0 to 1. And it's not going to, I guess it's 0 everywhere else outside of that interval, okay? And within that, basically you can have different kind of peaks here. All right, so if we go back to the baseball example, all right, basically we want our prior distribution selected so that pretty much almost all of the values are above 200 and most are below 300 and pretty much no one is above 400, okay? So we want everything to be kind of above 0.2 and definitely maybe to kind of max out around 0.35 or something, okay? And so to kind of get a distribution that looks something like that or fits those criteria, we might choose a beta distribution with shape parameters alpha equal to 81 and beta equal to 219, A equal to 81 and B equal to 219, okay? So these numbers are kind of arbitrarily selected. They're you know, there's no rule that says it has to be 81 and 219. Somebody else could pick different values. Maybe you could probably pick 70 and 200 or something like that. Okay. And you'll get similar distributions, but, you know, slightly different. But this distribution aligns with our prior knowledge. Okay. So all we said was that based on kind of what we know about baseball, that almost all the batters in Major League Baseball have batting averages over 200, and certainly almost everyone has batting averages under 350. Okay, or, you know, above 0.2 and less than 0.35. You know, what's a distribution that reflects that? And kind of, you can kind of pick some numbers to kind of get that. Now, if somebody decided on different numbers, but it has kind of a similar shape that kind of still fits this criteria, then that's probably also good. And so you might get a little bit of disagreement in terms of exactly what's the best way to, what should the prior distribution be? There might be a little bit of disagreement regarding what these numbers are. Oh, I totally forgot about the quiz. Okay. We will say today's quiz answers are B, C, and D. So bear, cat, dog. Okay, we will say that. I've got to create the quiz. I apologize. So, you know what? Today I'll go through and I'll create the quiz for I guess the entire quiz answers for all the for the entire quarter. But okay, so today will be bear, cat, dog. Okay, B, C, and D for today's quiz answers. Bear, cat, dog. Okay, is this all right? So this is just an introduction to kind of the idea that in Bayesian statistics, we're going to use a distribution to represent the parameter, and today is also just an introduction to the beta distribution, which is useful for situations where that parameter, that unknown parameter, is a proportion or probability. Okay. All right. So again, quiz answers: bear, cat, dog, B, C, D for questions 1, 2, 3, respectively. Okay. And we'll end there. Okay. So we'll so that takes us to the end of lecture, and we'll see you guys on Wednesday. I've posted homework 1. And so you guys can get started on that as well. All right.